Hello everyone, so we go over this time with the last section of infinite series and sequences. So we wrap up the chapter with a little bit more on Taylor series. I'm going to show you in this section how to find series representations of functions without going over the tedious process of finding multiple derivatives. Okay, so that is tedious, like I mentioned before. Okay, so I mean taking one derivative, two derivatives, but after the second, the third derivative, the process is just it's just tedious, and it leads to do a lot of uh, tedious calculations in plugging in values, taking derivatives, doing multiple product rules, and even um, quotient rules, chain rules. For example, look at these functions right here, the one that I'm highlighting. Okay, imagine, just think about these functions and how ugly would it be to go over the long process of finding a Taylor series by finding multiple derivatives? Product rule with an ln rule, and then this ln will turn into a quotient, and the problem is just going to become really ugly. Okay, the good thing about it is we have a power series representation. We have this table right here. So you might remember we did by hand the Taylor representation for the function e to the x, and that is x to the n over n factorial. Notice in this case I'm using the letter u. Your textbook, if you read your textbook, you will find this table. Actually, you will have a shorter table. Here I'm giving you a more complete table, so we can go over examples of more types of functions that the book doesn't do. And instead of looking at the letter u, you will see the x. However, um, we are going to get series for functions that do not have just x, but x squared or use x cubed, something other than just x. And in this case, we need a more general way to represent that. So that's why I'm using the letter u. And on top of that, these inequalities in parentheses right here are tells us the interval of convergence. So again, there's two things that we are going to do. Number one, we are going to convert to find a series representation in literally seconds, and we are going to find the radius of the interval of convergence, but we are not going to evaluate that tedious limit of a sub n divided by a sub n plus 1. We are given these intervals of convergence. We are just going to use them. By the way, this should be not an x but a u here. There's a little typo. This one should be a u, because u, again, that can be anything. Okay, u. So I'll show you a few examples. Okay, let me go over the first example. And f of x equals e to the 4x. Okay, how do we do this? Notice the amount of space that we have. It shouldn't take too many steps. All right, so in this case we have the function e to the 4x, and we are going to write the series representation without doing all these derivatives, tedious calculations. So I'm going to write the following: e to the 4x. Okay, so I'm going to have e to the 4x, and I'm going to represent this in terms of u, e to the simply u, where u is simply 4x. Okay, what is the series representation for e to the u? That is sigma n equals 0 to infinity of u to the n over n factorial. Now I'm going to substitute whatever we have for u, sigma n equals 0 to infinity of whatever u is, which in this case is 4x. And we're done, basically. Okay. Now all we have to do is distribute the power 4 to the n. Actually, not for n. This is supposed to be x, not n. X to the n divided by n factorial. Do you see how shorter is this? How easier it is in comparison with the long process? How long did it take in this case? Like I promised on the previous video, literally seconds. And that's all we do. Just use the table for Taylor series for known functions. And no matter what u is, the interval of convergence is negative infinity to positive infinity. Okay. Letter B. Okay, yes, it seems like really easy, but and yes, it is. However, you need to be careful when it comes to a function that is centered other than 0. Okay, careful here. Now the function is this. We want the series representation centered at x equals 3. This means that our series will have some x minus 3 to the nth power. Okay, but we don't have that x minus 3. We just have this e to the 3x. But I'm going to do a trick here. E to the 3x is the same as e to the 3 times x minus 3 plus 3. That's basically like adding 0 because negative 3 plus 3 it's the same as saying 0. Okay, and this is what am I going to do? I'm going to treat this as one single term, and then I'm going to treat this one as another single term, and I'm going to multiply this 3 times x minus 3 and 3 times positive 3. What am I going to get here? I'm going to get the following: e to the 3 times x minus 3 in parentheses plus 9. Okay. Now, by laws of exponents, when we have again a to the m plus n is the same as a to the m times a to the n. And I'm going to write this as e to the 3 times x minus 3 times e to the 9th. The idea is to have this x minus 3, that'll be the center of the series. What are we going to do with this e to the 9? This will be only a multiple constant, so that's why I'm going to use the commutative property of the multiplication to write the e to the 9th first, and then e to the 3 times x minus 3. Okay? Now, I'm going to set this u equals 3x minus 3. And we're going to have e to the 9th power. That is just a number. That's a constant. E to the u. So what do we know about the series for e to the u? Well, this is e to the 9 that multiplies the power series representation of e to the x, or e to the u rather, which is u to the n divided by n factorial. But what is u for us? So this is e to the 9th sigma n equals 0. So we are going to have 3 times x minus 3, the whole quantity to the nth power, divided by n factorial. Let's just simplify by distributing the powers here and there. So we are going to have the following: n equals 0, 3 to the n, x minus 3 to the n, divided by n factorial. And that's our final answer. Okay. Now, Look at letter A. That is the same one that we did on the previous section, and compare this final answer. You will find out that it's exactly the same. All right, letter C. What about the function f of x equals x squared plus 5x plus f of x equals x squared times e to the 5x cubed at x equals 0. Okay, the good thing, we won't need to find any shifting because it's centered at 0. We don't have to add that special version of 0 like the plus 3 minus 3 like we did on the previous example. Okay, so we are going to do the following. I'm going to write x squared e to the 5x cubed. Okay, I'm going to ignore the first x squared for a second. I'm just going to leave it x e to the u, where u equals 5x cubed. Okay, so that's a squared rather. Okay, so I'm going to go write x squared. And again, what is the series representation for e to the u? That's sigma n equals 0 to infinity of u to the n over n factorial. But what is u for us? Let's go back, substitute u to the n over n factorial. For us, our u was 5x to the third power. Okay, what are we going to do here? We are going to multiply, rather distribute the power. Okay, power of another power, multiply powers, so 5 to the n. I know there's this x squared still to do some work to it. We will get there sometime. We'll see what we do there. So this will be 5 to the n, x to the 3n. Power of another power, multiply the powers, divided by n factorial. Okay, because this series deals with x's, this is what I'm going to do. I'm going to put this x squared inside of the series. Okay, I'm going to put it inside, and this will be sigma n equals 0 to infinity 5 to the n times x squared times x to the 3n divided by n factorial. Okay, by laws of exponents, again, these two guys right here share the same base which is x. So all we do is add the powers. Equals 0 to infinity sigma 5 to the n x to the 3n plus 2 divided by n factorial. It took us at least a minute, maybe less than a minute, to solve this problem. Now think about doing this problem the long way. So just looking at this, you might want to you will have to do actually a product rule, and you don't want to do a product rule. Okay, and then when you take the second derivative, another product rule, actually multiple product rules, and so on and so on and so forth. You don't want to do that. Okay, let's do another example with an exponential function now with a bunch of negatives. Okay, let's look at this guy. This is telling us that there will be an x plus 4 to the nth power, because the center is negative 4, so the form of the series will be x plus 4 to the n. Okay, but in this case, we're going to do the same trick we did on part B of adding and subtracting the number, the center that we have in this case. Okay, let's see. So we are going to look for this guy, x plus 4. So this is what we do. E to the negative 6x equals e to the negative 6 times x plus 4 and minus 4. And I'm going to do the exact same thing. I'm going to group the first two. The first two terms, I'm going to take them as a whole, and the last term as only one term. Of course, it's just one. Distribute e to the negative 6 times x plus 4 Negative times a negative, this is 24 plus 24, and by the same law of exponents, I'm going to have e to the 24 that multiplies e to the negative 6 times x plus 4. Okay, so in this case, I'm going to take our u to be negative 6 times x plus 4. So this will be e to the 24th power times sigma n equals 0 to infinity of u to the n over n factorial. Okay, so let's just substitute for u in this case and put the e to the 24 inside of the series. So this will be sigma n equals 0 to infinity, not 1, I was going to say 1. So this is e to the 24 times the quantity negative 6 times x plus 4. Okay, and then divide that by n factorial. Okay, let's do one at a time. Again, keep in mind this negative sign. This negative sign is going to give rise to that negative 1 to the nth power times e to the 24 that we have, and then we are going to have this n to the 6 to the nth power times x minus 4 to the n power. And then you're going to have this divided by n factorial. Final answer. By the way, something I forgot to say, the interval of convergence, negative infinity to positive infinity. No big deal for e to the x. Whatever you put for u, it's always going to give us the same interval of convergence. It's going to change for other type of functions, as you will see. Okay, so let's look at another type of function. The function f of x equals 1 over 1 plus x. It's no longer e to the x in this case. It's going to be a different function. Let's go to the table to find out which function fits better for this function. And I'm thinking of this for number 2, in which we have any number in the numerator. The first term in the denominator has to be always 1. And we are going to have essentially a geometric looking sequence. Okay, now yes, in this case, let me just go ahead and do this and give you an example. But the trick is we have a positive sign here, and in accordance to our formula here, to our series, we must have a negative sign. How do we deal with that? Okay, let me show you. I'm going to do a trick. I'm going to change that plus into minus minus. So this will be 1 over, okay, well, yes, that's 1 plus x equals 1 over 1 minus negative x. Hopefully we all agree that minus minus, it's a smile rule that turns into a positive. Okay, so this is going to be sigma n equals 0 to infinity of a over 1 minus u, where in this case a equals 1 and u equals negative x. Okay, that is our substitution. Okay, so we are going to have sigma of a, which is 1 divided by 1 minus, wait a minute, no, this is not the series representation. Hold on, it's supposed to be a u to the n, my bad. So in this case, a is simply 1 times negative x to the nth power, which is this guy right here. I'm just going to highlight with yellow. Okay, so let's take care of this negative sign. So this will be sigma negative, n equals 0 to infinity, negative 1 to the nth power times x to the n. And that's the series representation for the function 1 over x. Okay? And in this case, notice the interval of convergence goes from -1, u is between -1 and 1. But in this case, what is our final u, which I'm going to highlight all the way here, by the way? This will be x lying between -1 and 1. You'll see how this is going to change in future examples, like letter F, actually. All right, what about letter F? Okay, letter F, let me write down the function again, 1 plus x under 1. But in this case, notice something. We have we want the series center at 2, not at 0. So this implies that we are going to have some x minus 2 to the nth power eventually. But I don't see that x minus 2 in our function, but we are going to make this happen. I'm going to write then 1 plus x minus 2 and plus 2. I'm going to add that. It's like adding 0. So I'm going to keep this as a single term, and I'm going to combine these two together. So 1 plus 2 equals 3. So this is 3 plus x minus 2. Okay, so that's the first trick we do. Okay. What is the other thing we need to do? Notice something here. This 3 is not supposed to be there. Let me go up to the series. Notice, like I mentioned earlier, this has to be always a 1. The first term in the denominator of that type of function has to be a 1. How do we get that 1 going? Well, I'm going to do the following. I'm going to multiply by 1/3 and divide by 1/3 to get this cancelled. So that's going to give us then 1/3 over 1 plus x minus 2 divided by 3. Okay, so far we're getting close to some sort of a divided by 1, but well, we are just missing the minus u. So I'm going to do another trick to get that minus show. Okay, so this will be 1/3 divided by 1 minus bracket minus x minus 2 divided by 3. So that's what I'm going to do. Okay, so this is our a, this is our u. Now we are ready to write this as a over 1 minus u, which in this case is sigma n equals 0 to infinity of a u to the n. What is a? A is 1/3, not 1 like on the previous example. Infinity. And u is this whole thing, negative x minus 2 to the n, not yet to the n, divided by 3 to the nth power. Okay, so this is what we do. This negative right here again will give rise to this -1 to the n power, the alternating factor. So this will be -1 to the n and times x minus 2 to the n divided by 3, the 3 that we have here, and then this 3 to the nth power. Okay, so we're almost done for this one, except we only need to combine these 3's. Notice they have the same base. They have the same base, and this is n equals 0 to infinity, and that's a -1 to the n, x minus 2 to the n power divided by 3 to the n plus 1. And that's final answer. Now, what about the interval of convergence? Well, so we know that for this series, according to the table, the interval goes from u being between -1 and 1. Let me set up an inequality. So -1 less than u less than 1. What is u for us? For us, the u is this quantity there. It's going to be there. So I'm going to set x minus 2 greater than -1 and less than 1. We are going to solve this three-sided inequality by adding plus 2 plus 2 plus 2. Okay? So the inequality becomes 1 less than x less than 3. So that is the interval of convergence for this series. Okay. Let's do another one. We are going to do a bunch of examples for this. We have, so you can see at least every single type of it, and then we're going to do this backwards as well. We're going to be given a series representation, and then we will find out what function is being represented by a given function. All right, so the next one, f of x equals 1 over 5 plus 4x, and in this case it's centered at x equals 2. Holy moly, okay, what are we going to do here? Well, number one, that x equals 2, the center, implies that we are going to have some factor of x minus 2 to the nth power. But I don't see that x minus 2, however, we can make that happen. How are we going to do that? Well, let's see. So I'm going to write the function 1 over 5 plus 4x equals 5 plus 4, wait a minute, plus 4 times x minus 2 and plus 2. That whole thing under 1. And I'm going to treat this as a single term. And I'm going to treat that as a second term. Okay. Before adding that 2 with the 5, we need to distribute this 4 times x minus 2, 4 times 2. Okay, so 5 plus 4 times x minus 2, 4 times 2, that's 8. 5 plus 8, that is going to give us a 13 plus 4 times x minus 2. And we're getting closer to what we want, to our form. However, number one, this has to be a 1. It is a 13. I don't want that 13 there. So we need to do a trick to make that 13 disappear, rather turning into a 1. So the trick is to divide and multiply by 1/3. 1/13th, rather, not 1/3, 1/13th. Okay. So when we distribute here 13 times a 13th, this gives us, okay, first of all, so this is a 1 plus 4 x minus 2 over 13 and 1 over 13 in the numerator. We're getting close, however, we need the minus sign here. So that is 1 over 1/13, 1 over 1/13th, 1 minus negative 4x minus 2 over 13. So now we have this a and u. Let's write this in the terms of a over 1 minus u, where this is, let me point it again, this is a and this is u. Okay, let's write this as a series. So this will be sigma n equals 0 to infinity of 1/13 times negative 4 x minus 2 divided by 13 to the nth power. Okay, let's fix this. Let's simplify this by keeping in mind that negative is going to give rise to that so-called -1 to the n, that alternating factor, and then this is going to be 4 to the n, then x minus 2 to the n, and then in the denominator, I'm going to have a 13 here first, and then another 13 to the n power, the one that comes from expanding this. And the only thing, the only one last thing we do is combine these bases together. The 1 to the n, 4 to the n, x minus 2 to the n, divided by 13 to the n plus 1. And that's final answer to this. Now the interval of convergence for this series, what is going to be? We said u between -1 and 1. And in this case, we have an x minus 2. And just like the previous example, add 2 to the 3 sides of the inequality to get 1 less than x less than 3. So that means that you can plug in any number between 1 and 3 without including the endpoints, and you will end up with a convergent series, like what we did on the previous section. Okay, let's look at another type of example, another type of function, one dealing with ln of x. Okay, let's look at the series representation for ln. Okay, so we have two different representations for ln. One for just ln of something, and another one for ln of 1 plus some u. Okay, again, just like on the previous example in the geometric type of series, we had to strictly have a 1 here, so we have to do it here. We have to have a 1 there. Okay, and it looks like it is the case for this example. We have that 1, so we're good. Okay, so let's start writing the function x cubed times ln of 1 minus 5x cubed equals, in this case, I'm going to set u equals, by the way, notice there is something missing here. There is missing, oh no, the plus sign is fine. What do we have here? Oh, we have a minus. Okay, we have a minus. We need to turn this into a plus. X cubed times ln of 1 plus negative 5x cubed. So in this case, our u will be negative 5x cubed. Okay, so let's turn this into series. Just focus on the ln, keep the x cubed for the end. We're going to incorporate it to add the powers of x at the end. So sigma n equals 0 to infinity of, in this case, I'm supposed to write this as, by the way, oh yeah, this one starts at 1, by the way. It doesn't start at 0. This is the first example that we will consider that starts at a different lower limit, and this is negative 1 to the n plus 1 over n, not factorial, just n, keep that in mind, and then u to the n. Okay, so what are we going to do? Plug in this u back in here. Okay, so this is x cubed sigma n equals 1 to infinity of negative 1 to the n plus 1 times negative 5x to the n, or x cubed to the n, divided by n. Okay, we need a bit of work here. Number one, let's look at this negative 1 to the n power, which will give us keep in mind the x cubed, I'll do that at the end. Negative 1 to the n plus 1 that came from the formula times negative 1 to the n times 5 to the n, and then x to the 3 times n. This will give us 3n. Divide that by n. Okay, I'm going to combine these two. Negative 1 to the n plus 1 times negative 1 to the n. That will add up to negative 1 to the 2n plus 1. And I'm going to incorporate at the same time this x cubed, and I'm going to put it inside here to multiply with this x term. So sigma n equals 0 to infinity. No, not 0, by the way. This is supposed to be a 1. Let me fix that on the previous steps. And this will be negative 1 to the 2n plus 1, 5 to the n, x cubed times x to the 3n divided by n. And again, all we do is combine these two powers of x. This guy with that guy, they're the same base, combine into a single base. So this is sigma n equals 1 to infinity, negative 1 to the 2n plus 1, 5 to the n, x to the 3n plus 3 divided by n. Final answer. What about the interval of convergence? Okay, according to our table, this is very similar to the geometric one, except that the upper endpoint has an inclusion of a less than or equal. Okay, so what do we do in this case? Simply u, which is less than or equal 1. So in this case, u is x from the last step of the series, not the one over here, because otherwise it will be a whole mess to write. So that's and that's our interval of convergence. Okay, let's look at another example. Now we are going to do a few more steps, a few more combinations here. We are going to add and subtract. All right, let's look at letter I. So notice we have 1 minus x and divided by 1 plus x cubed. Okay. So we don't have a power series representation for something like this. So in this case, I'm going to split this 1 minus x over 1 plus x cubed. I'm going to split it as 1 over 1 plus x cubed minus x over 1 plus x cubed. So in this case, we are going to have two different series at the same time. So we need a couple of tricks here. Again, keep in mind that the a over 1 minus u needs to have a minus sign here and a minus sign here, which is not there. Also, the numerator doesn't have x's, so I'm going to write it in front. Okay, so I'm going to do this. This will be 1 over 1 minus negative x cubed, the trick to turn it into negative, and then the 1 is already there, the number 1 that we need, no big deal, no need to do fancy divisions, and then minus x that multiplies 1 minus negative x cubed. So now we have this in the correct form. For both cases, notice this has a u of negative x cubed. Okay, so I'm going to use the power series representation for a divided by 1 minus u, which is sigma a u to the n power n equals 0 to infinity. I'm going to use that power series representation. So this will be for the first one, sigma for the first term. So 1 times negative x cubed to the n minus x times n equals 0 to infinity, 1 times negative x cubed to the nth power. Okay, so this will be for the first term. Again, this negative will give rise to those alternating factors, x to the 3n, and then minus, I'm going to incorporate this x, negative 1 to the n times x to the 3n. N starts at 0 to infinity, n starts at 0 to infinity. Okay, so what did we do? Put this x inside somewhere here, which is right there. So let's add the exponents to have everything in terms of a single base. So this will be equal to sigma n equals 0 to infinity of negative 1 to the n x to the 3n minus sigma n equals 0 to infinity of negative 1 to the n times x to the 3n plus 1. Final answer. Okay. Letter J. What about letter J? Well, in this case, we have some number to the x power. Well, this is an exponential function indeed. However, notice the base of the exponential is other than e. It doesn't match this form right here. It's not e to the u. It's some other base other than e. Can we do series representation for that? Yes, of course. We are going to use a little trick to get that done. So every time you have some a to the x power, keep in mind that the ln and e are inverses of one another. So the trick here is to do a to the ln of x. No, not a, hold on. It's going to be e to the ln of a to the x, because if this cancel, for example, e to the ln, we get back to simply a to the x. So we are going to do the reverse, and then we are going to have this jump to the front. So we are going to have some e to the x ln of a, and we will be able to use the power series representation for e to the u, which is this case right here. Okay, so you might want to keep this in mind. This is actually going to be a good exam question in which you might want to keep that in mind. Okay, so let me write down this 5 to the x in terms of a exponential of base e. So I'm going to do e to the ln, which is the inverse of 5 to the x power, and then we use what I call the Smackdown rule. What do I call the Smackdown rule or the basketball rule? Well, keep in mind that property of the logarithms in which you have ln of a to the x equals x ln of a. Okay, so essentially, if I do it this way, is Smackdown rule. Because this jumps right here. Otherwise, if we do it the reverse backwards to make this jump, we call it the basketball rule. It's like throwing to the basket, we're throwing the ball to the basket. So in this case, we're using the Smackdown Rule. So e to the x ln of 5. So in this case, our u will be x ln of 5. So e to the u, the series representation will be n equals 0 to infinity, u to the n over n factorial. That is sigma n equals 0. Our u in this case will be x ln of 5 to the n over n factorial. So let's distribute the power. So sigma n equals 0 to infinity of ln of 5 to the nth power, x to the nth power divided by n factorial. And that's how we get a series like this. Okay, so that's the trick. Okay, letter K. So f of x equals ln of 3 plus x centered at 0. Okay, number one, two things. I need this to be a 1. And I need this to be a minus. Okay, so there's two things I need to do. Okay, so I'm going to do a weird factorization for the inside of the parentheses of the log function. So ln of 3 plus x, I'm going to factor out the 3. This will be ln of 3 times 1 plus x divided by 3. Okay, so that's the weird factorization. And let me make this look nicer for the next step. And then this is what we're going to do. I'm going to do a property of logarithms, the property of logs that says that when we have ln of a times b, we can write this as a sum of two logs, ln of a plus ln of b. That is ln of 3 plus ln of 1 plus x over 3. This ln of 3, just leave it. I mean, don't erase it, don't get rid of it, just carry it. ln of 3, we're not going to do anything for the series. What we are going to do, we're going to work with this. So check mark, we already have the one we desired. We are only missing the negative sign. We're going to do that the usual trick. ln of 1 minus negative x over 3. And then let's do ln of 3 plus ln, not ln anymore in this case. Let's write this in terms of u. This is u. So the series representation for ln will be sigma n starts at 1 to infinity, negative 1 to the n plus 1 of u to the n divided by n, not factorial, just n. So let's go back substitute this u over here. Okay, ln of 3 plus n equals 1, negative 1 to the n plus 1. This is going to be negative x over 3 to the n divided by n. And this is our back substitution for u. Okay. Wait a minute, I don't think we needed the minus though. Let me go back. No, we didn't need a minus. The plus was correct. The plus was fine. Okay, so let me take a few steps back real quick. Let me take this back. Sorry about this. No more. All right, this so no more trick right here, so we can go straight to the series representation. N equals 0 to infinity. not 0, but 1. And this is -1 to the n plus 1, x over 3 to the n over n, just n, not n factorial. Now we do the following. I'm going to do ln of 3 plus sigma n equals 1 to infinity of -1 to the n plus 1 over n. This is x to the n over 3 to the n. And that's all we do. We're done for this one right here. Put this together as a multiplication, okay? And that's about it. Okay. Okay, what about f of x equals x cubed times sine x to the 7 at x equals to 0? Interesting. Okay, now we're going to look at a different type of series, in this case, the sine function. Okay, let's go up to the table. So the table for sine of u will be sigma -1 to the n times u to the 2n plus 1 divided by 2n plus 1 factorial. Okay. First of all, from here, I'm going to say that u equals x to the 7. And I'm going to write this x cubed simply in front of the sigma notation, n equals 0 to infinity -1 to the n times u to the 2n plus 1 divided by 2n plus 1 factorial. But what is u again? Let's highlight where it corresponds to be a u. Don't forget this x cubed in front. And this is substituting -1 to the n, u to the 2n plus 1, where u equals x to the 7th, this one right here, divided by 2n plus 1 factorial. So before incorporating this x cubed, I'm going to simplify this x to the 7 times 2n plus 1. Okay, so I'm going to do this on the side. The power of another power multiply the power. 7 times 2n plus 1 is the same as saying 14n plus 7, which I'm going to write on the next step. So x cubed sigma n equals 0 to infinity -1 to the n x to the 14 n plus 7 divided by 2n plus 1 factorial. Okay, I'm going to incorporate this x cubed inside. Okay, just a couple more steps and we're done with this guy right here. So n equals 0 to infinity -1 to the n x cubed x to the 14 n plus 7 divided by 2n plus 1 factorial. And I'm going to combine everything in terms of a single base. So I'm going to add x cubed x to the 3 plus 14 n plus 7, which will give us sigma n equals 0 to infinity -1 to the n x to the 14 n plus 10 divided by 2n plus 1 factorial. Final answer. All right, so what if we have a trigonometric function and we want to develop a series that is not centered at 0 but centered somewhere else? For example, like letter M. The following center at x equals pi over 3 implies that this must have this must have sum x minus pi over 3 in our parentheses. But notice it's missing here. It's missing there. However, before showing you how to work with those type of shiftings, I need to show you these few trigonometric identities for the sum and difference of angles. So if we have the sum or difference of sine and of sine, we are going to have sine alpha cosine beta plus minus. Notice the plus goes with the plus, the minus goes with the minus. Cosine alpha, sine beta. Otherwise, when we have cosine, in this case, the plus minus gets inverted. If we are given a plus, then we change to minus. If we're given minus, we're given a plus. We turn into a plus. Let me give you a quick example. Suppose we have sine of x squared plus y cubed. This will be, this is our alpha, this is our beta. So this is going to be sine alpha, which in this case is x squared, sine of x squared, cosine y cubed plus cosine alpha, which in this case is x squared, sine beta, which is y cubed. Okay, another example, cosine of, I don't know, the same, why not, x squared, and I'm going to be having a plus again, x squared minus y cubed. This will be cosine alpha, which is x squared, times cosine beta, which is y cubed. But the plus turns into a minus according to the symbols here that I highlighted. Minus sine alpha, which is x squared, sine beta, which is y to the third. We need to use the trigonometric identity to simplify the following exercise. So I'm going to start writing cosine of x as x minus pi over 3 plus pi over 3. Okay, and I'm going to treat the first two terms, x minus pi over 3, as a single term, in which this will be our, let me use blue instead so it highlights better. Well, this will be our alpha and this will be our beta. So for cosine, I'm going to have cosine alpha, cosine of x minus pi over 3, cosine beta, which is cosine of pi over 3. And then because of this plus, we're going to have a minus there. Cosine, but not cosine, that's going to be actually sine. Sine alpha, which is sine of x minus pi over 3. Sine beta, which is sine of pi over 3. Okay. Now, let's evaluate each of these. For example, this one right here, cosine pi over 3, can be evaluated using the unit circle or the triangles, whatever you use for those. So I'm going to write the answer as a coefficient actually, and this will be the square root of 3 over 2 cosine of x minus pi over 3. Where did I get that cosine of pi over 3? I got it from here. Okay, so you can relate. Actually, let me use a different color over here so it doesn't get confusing. This guy, I'm going to put it in green. Why not? Green. And this will be 1/2 minus 1/2 of sine of x minus pi over 3. Okay, so in this case, we are going to use both series at a time. The series for cosine and the series for sine. Okay, so lucky for us, u equals u equals x plus, x minus whoops, what happened here? X minus pi over 3. Okay, so I'm gonna write the square root of 3 over 2 sigma, the series for cosine. Let me go up to show you the series for cosine and show you how different it is from that series of sine. Cosine. It looks very similar, except the power of u, which instead of being 2n plus 1 like in sine, it is just 2n. Same for the denominator, the factorial is 2n factorial, not 2n plus 1. So let's this will be negative 1 to the n, u to the 2n for cosine divided by 2n factorial, n equals 0 to infinity, minus 1/2 sigma n equals 0, negative 1 to the n, u to the 2n plus 1, because that's for sine, 2n plus 1. So we use both at a time. Okay, and let's just plug in what u is, which in this case u equals x minus pi over 3, x minus pi over 3. So square root of 3. We actually incorporate it. Okay, sigma n equals 0 to infinity, negative 1 to the n times square root of 3 times x minus pi over 3 to the nth power divided by 2 times 2n factorial. And be careful, these 2's don't multiply, because the 2 right here inside of the parentheses is protected by the factorial. Okay, so minus sigma n equals 0 to infinity, negative 1 to the nth power, x minus pi over 3 to the 2n plus 1. By the way, this should have been 2n, not just n. Let me erase this and change. This is 2n divided by 2 times 2n plus 1 factorial. Actually, this 2 doesn't distribute. And that is the series representation of cosine at x equals pi over 3. Let's look at another example, letter n. For letter n, you are going to have one like this on the homework, on the textbook homework, in which you will need to expand a few terms of the series and see what happens. So let me, by the way, there's a little typo here. This is supposed to be not x to the x, but e to the x. I think your notes have been updated with the e to the x, so it represents the change. So this is what we are going to do here. Okay, I'm gonna have 1/2 times the series representation for e to the x, which is simply x to the n over n factorial, and starts at 0 to infinity, minus sigma n equals 0 to infinity of negative x to the n over n factorial. I know you might want to distribute the 1/2, but I'm not going to do, because it's going to cancel a few steps further. So that is 1/2 sigma n equals 0 to this infinity. Okay, it's still the same, x to the n factorial. And for the next, I'm going to have negative 1 to the nth power, x to the n over n factorial, n equals 0 to infinity. Okay, I'm going to expand a few terms for each. So this will be 1/2 1 plus x squared over 2 factorial, which is 2 plus x cubed over 3 factorial. And it will be the same, except for, be careful here, this is minus 1 minus x plus x squared. Oh, by the way, I needed to add that dot dot dot. You know what? Let me add a couple more. Let me add, so plus x to the 4th over 4 factorial. Typically we don't go that high, but in this case we will need plus dot dot dot. And then minus the series representation for this one, that is 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot dot dot. Okay, what is going to happen in this case? I need you to observe something. Remember telescoping series? So let's see. In this case, notice, I would like you to notice the following. Notice how this 1 minus 1 cancels, and then this x squared over 2 factorial cancels, the x squared over 2 factorial, x to the 4 over 4 factorial cancels the x to the 4 over 4 factorial, leaving us with the following. This will leave us with 1/2 times x plus, well, actually not x, actually in this case, let me highlight this, x minus negative x, that'll be plus x, which will give us 2x. And then x cubed over 3 factorial minus negative x cubed over 3 factorial would give us 2 of them. I'm going to highlight those with green so you can see how am I adding them. So this will be 2 x cubed over 3 factorial, and so on, so forth. Okay, notice we can divide out these 2 right here with that 2, leaving us with simply x plus x cubed over 3 factorial. If we continue this pattern, we would have plus x to the 5th over 5 factorial, because notice the odd powers and the odd factorials. The invisible one is the same as 1 factorial, and then x to the 7 over n factorial, and so on and so forth. So in this case, we are going to have sigma, in this case, no alternating factor because all of them are positives. This will be x to the 2n plus 1 divided by 7, 2n plus 1 factorial, starting at 0. Okay, so you will see a similar example on the homework. Now let's do it the other way around. Now we'll look for functions. We're looking for, the series. Now they're asking us to find the functions being represented by those series. So notice this x over 2. That reminds me to the geometric series. How? Well, the trick is, if we write this as x over 2 to the nth power, okay, so we are going to have a u equals x over 2. So sigma of u to the n with a 1 in the front, this is our a over 1 minus u, but a for us is this one right here, and this u is right there. So the function represented by that series will be 1 over 1 minus x over 2. And you might want to simplify the complex fraction by multiplying and dividing by 2. So this will give us 2 over 2 minus x. Okay. All right. What about the next one? Well, the other one, believe it or not, it's like a geometric series in disguise. However, what calls my attention here is the exponents of x and the exponent of 4. So I'm gonna do a little trick here. To write x to the 2n as x squared to the nth power. Okay, because the power of another power multiply the powers, n times 2, that's 2n, that's 2n that we have here in highlighted in yellow. So this is 4 to the n still. And now we may group this into a single ratio and write it as a geometric form. So we are going to have -1 to the n. Actually, everything has n power. If you notice, everything has n power. This n right here, this n right there, this n right there. So we can just write everything inside of a big parenthesis, negative x squared to the 4 to the n, in which this is our invisible one, our a, and then 1 minus u, whereas u equals negative x squared over 4. So this will be our a, and this will be our u. So what is the function being represented? This will be 1 over 1 minus negative x squared over 4, which is the same as saying 1 over 1 plus x squared over 4. You might want to multiply numerator and denominator by 4 to cancel or to simplify that complex fraction. That'll give us 4 plus x squared and under a 4. Okay. All right, the next one. What about the next one? Well, that one may not be that straightforward. We may need to do some work here. Okay. This one will require a little bit of work. I'm going to use laws of exponents backwards. Sigma n equals to 0 to infinity, 2 to the n, x to the 2n times x to the first power. Okay. Then I wish I had everything in terms of the power n. So the other thing I'm going to do, just the same way we used to incorporate x's inside of the series, I'm going to de-incorporate. I'm going to do the reverse. I'm going to take this out because ultimately the series is in terms of n, not in terms of x. So x is basically constant in term for our series. And then I'm going to write x times sigma n equals to 0 to infinity. This is 2 to the n, and this is x squared to the n. Now that we have the same power, n and n, we can put everything in terms of a single u. Okay. So this is 2x squared to the n, where this is there is an invisible one here, and u equals 2x squared. So this is the same as saying one over 1 minus a, rather, not 1. Minus u, where this is a and this is u. So let's write this as, and don't forget this power of x multiplying. Okay, actually let me make some room here. So I'm gonna write this equal, put a bracket around the a over 1 minus u, and carry this x, put it in front. This will be x times 1 divided by 1 minus 2x squared. So the function being represented in this case, so just multiply x times 1 to make this look nicer, x over 1 minus 2x squared. Okay. If for fun you want to do it backwards to see if you get the same series, try it like the exercises that we did before we moved on to this. Okay. Letter D. What about letter D? Okay. All right. So letter D, what stands out to me is this 2n factorial, which is very characteristic of the cosine function. However, the cosine function has a 2n, right? It has a 2n as a power, but here we have a 4n. How is that going to make a difference? Okay, so we can rewrite this as -1 to the n power. Hopefully we all agree that 4n is the same as saying 2 times 2n. 2n factorial, which equals n equals 0. So when we have the power, okay, let me write the law of exponent. X to the a b, this is the same as x to the a to the b, or x to the b times a. Either way, in this case the multiplication is commutative, so what I'm going to do here is rewrite this as -1 to the n times x squared to the 2n divided by 2n factorial. And now you can see what the u will be. Okay, so we have this 2n factorial and 2n, the 2n and 2n factorial that are characteristic of the cosine function. Can you see this? So 2n and 2n factorial. Okay, let's keep simplifying this one. All right, so this will be cosine of u, simply cosine of u, where u is the quantity highlighted in yellow. So all we do here is cosine of x squared. All right, let's look at a couple more, and then we move on to applications to evaluating integrals using series. Okay. All right. So let's see, what do we have here? So here I have there's something kind of weird going on here. Okay, number one, there is another silly typo here that I needed to fix. Hopefully on your paper is fixed. This is supposed to start at 1 originally. Okay. Now, what are we going to do here? Well, remember when we shifted series, if I subtract 1, I need to add 1 to any other instance over here. Okay, to all ends. And the trick here is n equals to 0. That way we have a series starting at 0, and then you will see where it is going to go, -1 to the n, because 1 minus 1 cancels, 1 minus 1 cancels, 1 minus 1 cancels. Okay, so we are going to have 2 to the n divided by n factorial x to the n plus 1. Hopefully this looks familiar to you, the n factorial in the denominator. The n factorial in the denominator is very characteristic of the function e to the x, which is sigma n equals 0 to infinity x to the n over n factorial. However, look at the power of x to the n minus 1. We wish we had it as just n, and we can make that happen. N equals 0 to infinity, negative 1 to the n, 2 to the n, x to the n plus x. I mean, not plus x, actually, times x over n factorial. And again, the dummy variable for the series is n, not x, so I'm going to de-incorporate this x and put it outside of the series as a multiple constant. Okay, now this will be x sigma negative 1 to the n, 2 to the n, x to the n over n factorial. I'm going to group everything in the numerator to have everything under some n. So this will be, don't forget the x, just keep writing it. N equals to 0 to infinity. This is going to be negative 2x. Negative 2x to the nth power over n factorial, where the negative 2x will work as our u afterwards. Okay, so x, this is equals to x times sigma n equals to 0 to infinity of u to the n over n factorial, which ultimately will be x e to the u. So in this case, let's highlight this with yellow just to show you where it is going to go and where is this coming from. Okay, so finally x e to the negative 2x is the function being represented by the given series. Okay. Another interesting one, one involving natural logs. Okay, so this one, this is what are we going to do. I'm going to group these 5/7 to the n with x to the n. So this will be ln of 7 plus sigma n equals 1 to infinity, negative 1 to the n plus 1 divided by n, and this will be 5/7 of x to the nth power. So this looks like our u. This looks like our u. So this will be ln of 7 plus ln of 1 plus u, where u will come from here, the number inside of the n power. So ln of 7 plus ln of 1 plus 5x over 7. So we're almost done, except that we are now going to use the properties of logarithms for the addition, turn it into a multiplication, just like we did on the previous example on a couple pages ago. I'm going to do it but backwards. Ln of a plus ln of b equals ln of a b. This will be ln of 7 times not x, and 1 plus 5x over 7, and all we have to do here is distribute the 7, giving us ln of 7 plus 5x. Final answer. So ln of ln of 7 plus 5x is being represented by this series right here. All right, so this is it for as far as looking at functions and represented in terms of a power series, and the reverse. Given a power series, what is the function being represented by that series? Now, how can we apply this to integration? Remember that. Remember this integral. E to the x squared. Remember that we cannot do u equals x squared. Well, I mean, you might want to do it, but when you do the u, you get 2x dx. But we're missing some power of x here, and because of that reason, we weren't able to evaluate that integral. So we are going to do that integral using series. Okay, so we are going to do the following. I'm going to write the integral of the series representation of e to the x squared, which will be x squared to the n over n factorial. N starts at 0 to infinity. Okay, keep in mind that this is our u. This is our u. And it would go over there. So this will be. I'm going to do something to avoid too many symbols, to avoid confusions with too many symbols, actually. I'm going to flip the order of between the summation symbol and the integral. This can be done. And this is x to the 2n over n factorial dx. Actually, I forgot the dx here. Notice the variable is x right here. So what I'm going to do as well to get this easy to visualize, one over n factorial times the integral of x to the 2n dx. Okay, and now we're going to use the general power rule to evaluate this integral. So we are going to have sigma n equals 0 to infinity n factorial under 1, and using the general power rule, add 1 to the exponent, divide by the new exponent, that is x to the 2n, plus 1, divide by 2n, plus 1, plus c. So what I'm going to do, just put everything together into a single fraction. So the integral of the function e to the x squared is given by a series expansion, not by some known function. So we're going to leave it like till 2n plus 1 times n factorial, all under x to the 2n plus 1, and don't forget the plus c. Done. Okay. How to evaluate the following integral? Well, sine of x to the 4 sine of x cubed times sine x to the 4 times sine of x cubed. Yes, that's correct. Okay, if we do the u substitution, u equals x cubed, the u 3x squared. Well, notice the power is to the 4, so we are not going to be able to do this. And I don't know if integration by parts, but look at this. Integration by parts is just going to be a total mess. I don't think it's going to work though, just to be honest with you. Okay, so this is what we do. We are going to write x to the 4th times sine, the representation for sine, which is n equals 0, that's -1 to the n, times did I use u? Well, yeah. So in this case, x cubed to the n, 2n plus 1 rather, over 2n plus 1 factorial. That is the series representation for the function sine of x. But in this case, our u is not just x, but actually x cubed. First of all, we need to do some simplification. We need to do some work before we are able to integrate this. So this will be x to the 4th times sigma n equals 0 to infinity. And I'm going to write this 2n plus 1 times this 3. This will be 6n plus 3. So I'm going to have x to the 6n plus 3 over 2n plus 1 factorial dx. I forgot the dx over here as well. So, what's next? This will be integral of, I'm going to incorporate this x to the 4th over here. And I'm going to add it with the constant 4 plus 3. This will be x to the, hold on, did I make a mistake on my notes? Yes, I did a silly mistake on my notes. I forgot. Never mind. This one is correct. So this will be sigma n equals 0 to infinity. Because on my notes I didn't replace the u with x cubed. I left it at just x. So my bad here. All right. So this will be, I forgot the -1 to the n. -1 to the n, x to the 6n plus 7 divided by 2n plus 1 factorial. Before integrating all this, I'm going to take out everything that doesn't depend on x, and I will also reverse the order of the summation and the integration. Times the integral, no limits in this case, so x to the 6n plus 7 dx. So all we focus is on this integral right here. To add 1 to the exponent and divide by the new exponent. So if we add 1 to the exponent, what do we get? Plus 1, that's a plus 8. We get a plus 8. So n equals to 0 to infinity, -1 to the n over 2n plus 1 factorial times x to the 6n plus 8, add 1, 6n plus 8. Do that in the denominator as well. Okay, so this will be equal. Let me just write it to a single expression. By the way, I forgot the plus c. This will be sigma n equals the 0 to infinity of -1 to the nth power x to the 6n plus 8 divided by 2n plus 1 factorial times 6n plus 8 plus c. Hopefully I didn't make a mistake. If so, we can discuss it later. All right. And that's what we get. That's the integral of that function in terms of series. Okay, last example. Last example is to evaluate a definite integral. Okay, so they're asking us to use a 21st degree Taylor polynomial to evaluate this integral. All right, when you read this 21st degree Taylor, that we're talking about a polynomial of degree 21. No, it's not what you're thinking. We are not going to take 21 derivatives and then come up with a series. We're going to do a way shorter trick. Actually, we are going to take advantage of this of the series expansions for the known function. So sine of x cubed is the same as saying sigma n equals 0 to infinity of -1 to the n x cubed to the 2n plus 1, where in this case what I'm highlighting is the u. Okay, and divided by 2n plus 1 factorial. All right, So let me simplify first. N equals 0, infinity, negative 1 to the nth power, and this will be x to the 6n plus 3, okay, divided by 2n plus 1 factorial. All right, so I'm going to expand a few terms, not 21 terms either. You'll see what do I mean by first degree, by 21st degree. Oops, 21st degree. So for n equals 0, if I use n equals 0, I get negative 1 to the 0, which is positive 1. 6 times 0, which is 0 plus 3. I'm going to get, well, let me actually write everything down. Why not? Negative 1 to the 0 times x to the 6 times 0 plus 3 divided by 2 times 0 plus 1 factorial, plus for n equals 1, I'm going to have negative 1 to the first times x to the 6 times 1 plus 3 divided by 2 times 1 plus 1 factorial, plus for n equals 3, no, not n equals 3, what am I saying? N equals 2. So for n equals 2, I'm going to get negative 1, oops, not red, negative 1 to the second times x to the 6 times 2 plus 3 over 2 times 2 plus 1 factorial. And for n equals 3, we get negative 1 to the third plus 6 times, x to the 6 times 3 plus 3. Actually, not plus. Give me a second. Oops. Times x to the 6 times 3 plus 3 divided by 2 times 3 plus 1 factorial equals. Okay, let's simplify this and see what is going to happen. I'm going to leave only 4 terms. Hopefully, we're lucky enough to have the 21st degree Taylor polynomial. So here I'm going to multiply 6 times 0, which is 0 plus 3. I'm going to get an x cubed. 2 times 0 is 0 plus 1. 1 factorial, which is 1. And negative 1 to the 0, it's a positive 1. Okay? So I'm going to leave the 1 factorial. I'm going to leave everything in terms of factorials for a second. Plus negative 1 to the first is going to be a negative 1. X to the 6 times 1, which is 6 plus 3, that's 9. Over 2 times 1, which is 2 plus 1, 3 factorial. Plus negative 1 squared, that's a positive 1. And 6 times 2, which is 12 plus 3, that's x to the 15, divided by 2 times 2, which is 4 plus 1, 5 factorial, plus negative 1 to the third power, which is negative 1 times 6 times 3, which is 18 plus 3, that's the 21st degree polynomial I was talking about. 2 times 3, which is 6 plus 1, 7 factorial. So again, when we look at the instructions, it might sound harder and tough and tedious, more tedious than it actually reads, but it's not, because ultimately we're using only 4 terms. Okay, 4 terms only. Okay, so plus dot dot dot. So actually, I'm not going to use even that plus dot dot dot, because we are only getting the 21st, actually the P21, which is the polynomial of 21st degree. Let me simplify that. P21, that's x, that's an x cubed minus x to the 9 over 3 factorial, which is 6, plus x to the 15 divided by 5 factorial, which is 120, minus x to the 21st power over 7 factorial, which is 50, 40. Big number. All right, now let's go back to the integral. So the integral from 0 to 1 of sine of x cubed dx will be the integral from 0 to 1 of p21st dx, which in this case is this quantity right here. We're going to integrate that term by term. 0 to 1, x cubed minus x to the 9 over 6 plus x to the 15 over 120 minus x to the 21 over 50, 40 dx. So we integrate each term at a time. We should get x cubed over 4 minus x to the 10th over 60 plus x to the 16 over 1920 and minus x to the 22 divided by 110,880. That evaluated from 0 to 1. Okay, so applying the upper limit first, we get 1 cubed minus 4 minus 1 to the 10th over 60 plus 1 to the 16th over 1920 minus 1 to the 22nd power over 11,880. That's the upper limit minus the lower limit. But do you notice that if we plug in 0 everywhere, all these terms go to 0? So all we have to do is just write down a big 0. Using a calculator, you should get 20,743 divided by 88,704, which is approximately 0.234. And this is how we evaluate a definite integral using power series. Because again, we cannot integrate sine of x cubed because of that power. If we have only sine of x, well, we just do that. Okay, and in the instructions for a typical problem like this, they're going to ask us for which Taylor polynomial to use, which is going to be related to how many terms that we need to develop for a given series of representation for the function that we want to integrate. And this is the end of the section, which is actually the end of the chapter. So one more chapter to go. So see you in the next chapter.